You gotta look online, Google Classroom, Remind. All right, so 85 was a fraction problem. 86 was also a fraction problem. And number 85 was the difference quotient. Oh.
Your board is the slacker today.
I know.
Slacker.
Give up. It's like a game. It's like how fast you
Target. Okay, there we go. All right, so, come on, buddy. I think it was 1 over t.
Yeah.
Yep.
Yes.
And then I wanted you to find f of t minus f of 1 all over t.
I think it goes over T minus 1.
T minus 1? All right.
Is that right?
I have it. Yeah, sounds good. So it is a fraction to begin with, and then you're applying the difference quotient, which is also a fraction. So we're going to have like a fraction in a fraction, which last year we said was a complex fraction. So the difference quotient part says take f of t. So we have to start with this piece, f of t. And apply that to 1 over t. Well, there's nothing to apply because there isn't anything different in the parentheses. So what represents f of t? 1 over t. So instead of f of t in the difference quotient, we're replacing that with 1 over t. As nothing is being changed if there isn't anything different inside the parentheses. If there was an x inside there, or a number, or an x plus h, then we'd replace the t with x plus h, but there's not. So we have that 1 over t. Then it says subtract f of 1. So if we're finding f of 1, Ben, I know you weren't here yesterday, but what would you do to evaluate f of 1?
So you would make it 1 over 1.
Yeah, 1 over 1. Because f of t is 1 over t. There's a 1 inside, so you're replacing that t with a 1. And 1 over 1 becomes 1 over 1, or just 1. You want to leave it as 1 over 1, so you have a fraction minus a fraction. In the denominator, it says t minus 1. So that's on the bottom. So the top part is the difference piece, taking the difference of f of t minus f of 1, and then we're dividing that by the t minus 1. So because there's a fraction in the numerator, just looking at the numerator part, this box up here, we need to combine those by getting a common denominator. So if you have 1 over t minus 1 over 1, what would you use as a common denominator? Jacob? T. So that means the top needs a t and the bottom needs a t, so that it has the common denominator. So we have 1 minus, this now says t, because we multiplied by t. The denominator, they're both the same, therefore we can do the subtraction, so that's a t. And then down here is still t minus 1. So this is a complex fraction because you have a fraction on the top and you still have something in the denominator. So all I did with the top was get a common denominator to try and combine those two together. Questions?
Wait, and that's your final answer.
It is not your final answer because it can still be simplified. So in the numerator part, just looking at the 1 minus t, it's really similar to t minus 1, but not quite the same. What could you do to make them the same? Jacob? So he said multiply by a negative, or you could think the opposite. You could pull out a negative. So factor out a negative so that they become the same. So instead of having 1 minus t, if you factor out a negative 1, so pulling out a negative 1 gives us a positive t, and then this becomes a minus 1. Because these quantities are essentially exactly opposite of each other. So t minus 1 and 1 minus t are opposites. So if you pull out a negative 1, now they're the same. When they're the same, what happens, Greg?
Well, the t minus ones would cancel out.
Yeah. So the t minus 1's cancel. You're left with a negative 1 and a t. What can't t be?
0.
Not 0. 1.
One.
Nice.
Great.
Nice job, twins. Good job.
But like,
Teamwork.
but now it can also be 0, right?
Yeah,
Well,
but
now
I
it
was-
can't also be 0, yes.
Okay.
So Gray said, yeah, but it still can't be 0 now because it's still in the denominator. And Gray's right, yes, it still can't be 0 now.
Chance.
Questions? So number 86 was very similar. And again, I have it worked out. So look at Remind, look at Google Classroom, but the process is the same. It's just using x minus 4. X there, the 7, x minus 7. So it's f of x minus f of 7 divided by x minus 7. But the process is the same, it works out the same. Like things cancel the same way. Are there any questions with the domain and range problems? 56?
No,
65. 65, the calculator one, I think?
no,
Yes? No?
no, 63.
63. Okay. Because I think 65 is the calculator one. Pretty sure. Alright, so 63, we have g of y, and then y plus 2 divided by the square root of y minus 10. Alright, so two things to think about for restrictions. If you have a denominator, it can't be 0. If you have a radical, it has to be greater than or equal to 0. How does that apply to this problem? Yeah, it's both. So, because the radical is in the denominator. So, the radical has to be greater than or equal to 0, but the denominator can't be 0. So, what does that mean about the radical on the bottom? Jesse?
It has to be greater than 0.
It has to be greater than 0. It can't equal 0 because if it was 0, then it would be undefined. So that means it just is allowed to be greater than 0, not greater than or equal to. And then if you solve that little expression underneath there, that means the y has to be greater than 10. So it can't equal 10 because if it was 10, 10 minus 10 is 0, the square root of 0 is 0, and now I have 0 in the denominator. It's allowed to be bigger than 10 because 11 minus 1 is the square root of 1. You can have a 1 in the denominator. It can't be less than 10 because if I plug a 9 in, 9 minus 1 or 9 minus 10 is negative 1. And then we have the square root of negative 1, which can't also exist. So if y is greater than 10, that means it starts at 10 and it goes to positive infinity.
That's pretty radical.
So it can't equal 10 because then it would be 0 in the denominator. It can't be less than 10 because then you'd have an imaginary number. Therefore, the only option is for it to be greater than 10. Questions? So I know the two side rows yesterday. I didn't look at yesterday's homework. So if you could just keep that on the side of your desk, please. I'll come around and check it. Dan, you weren't here yesterday, so you can get out yesterday's homework as well. Come around and check that. Dan, you're looking pretty classy today. Yeah.
Am I more well-dressed than well-dressed Chandler?
Oh, maybe.
Today
Maybe.
you are.
You got a collared shirt on and everything?
Slacker Chandler.
Yeah.
Just let yourself go.
All right, so in your notes packet, if you'll turn to section 1 of 3. Today we're just going to look at the graphs of the function. So if you want to grab your graphing calculator, we'll use that just a little bit to remind you about looking at a couple of pieces in the calculator, the graphs. So section 1-2 was working with evaluating the function based off the equation. Determining if it was a function based off of the equation. Finding the domain of the function based off the equation. So Friday and yesterday, all dealing with the equation. Today we're gonna look at the graphs of those equations, finding the same things, but now trying to use the graph. So instead of having an equation, what does the picture tell us? So if you look at example 1, given the graph, find the domain, find f of -1 and f of 2, and then find the range. See if you can find those three pieces. So the domain of the given graph is exactly the same in your page. F of -1 and f of 2. We don't have an equation to plug in -1 and 2. We have a graph to look at. And then find the range. Alright, so how about the domain? Domain of the x values from left to right. So it's the horizontal distance that the graph would be defined. Great, what do you think?
-1, 4, the bracket on the -1, and parentheses on the 4.
So using your x values, it starts the x value of -1, it goes to the x value of 4. But you said a bracket with the -1 because?
Because it's colored in.
Right, and a parenthesis around the 4
So,
because there's an open circle. So the range or the domain is the horizontal distance of the graph, that space that it's taking up. The second one, it says find f of -1 and then f of 2. There's not an equation to plug in. How do you find f of -1? Jacob?
-1 is an x value.
So you're really finding it's matching
-5.
-5, which is the y value. So you have x, you're finding y. So x is -1, the y he said was -5. At f of 2, Jacob, the y value is?
4.
Is it 4 on yours?
yes.
Yeah, okay. Mine should go up to 4 then. Just make it go up there. There we go. I'll fix it later. So you know x, find y. That's what f of x means. So you know your x value, find its matching y value. And then the last thing, make sure you're using your graph for the range. The range would be the vertical stretch of the graph. So Grant, what would the range be here?
-5, +4, both in brackets.
Nice. So he said -5, +4, both brackets, because they're both ordered pairs on your graph. Points that exist, closed circles. Questions? What's the vertical line test do? Chandler said it tells if the graph is a function. Sean, how does it tell if the graph is a function?
If doesn't move through 2 points on the same x value, then it's a function. Then it's not a function.
So we draw vertical lines. And he said they must pass through the graph one time for it to be a function. So if it passes through the graph once, it's a function. More than once, it would not be a function. So when you're looking at the graph, you draw vertical lines, little vertical lines, imaginary vertical lines, invisible vertical lines. Make sure it passes your graph lines for it to pay attention. Questions? Alright, so increasing and decreasing intervals of functions. So if you look at a graph, you read a graph from left to right. So always from left to right. From the left, if the graph goes up, we say that's increasing. If it goes down, that's decreasing. So we're going to kind of describe increasing and decreasing intervals. So make sure you kind of note that it's from the left to the right. So we'll say are described or defined using x values. So essentially you're looking for the domain of the portion that's increasing and then the domain of the portion that's decreasing. But when you describe them or you define them, you're saying this horizontal distance of the graph is increasing. Even though you're looking vertically up and down, you're saying how far left and right the piece would be going up, or how far left and right the piece would be going down. So in example 2, it says find the interval, or intervals, where the graph is increasing or decreasing. So reading it from left to right, I hope I have the same graph as you.
Yes.
Yes? Good?
Yes.
Okay.
We only have the 2 points that are like.
You, the max and the mins?
Yeah.
Okay.
But
But the max and the mins are correct.
And it's still the same.
Okay. So if you're finding an interval where, we'll just start with the increasing, where it's increasing. Where do you think a graph stops increasing? So if you're reading it from left to right, how do you know where that point is where it doesn't increase anymore? Jesse? The max, yeah. So the max of the graph, right here, in this case it's -1, 2. That's called our turning point. That's the location where the graph no longer is increasing and it decides to go down and switch locations. We have another turning point at 1, -2, because that's the min of the graph. So the graph stops increasing and it becomes a decreasing section at its turning point, the point where it changes directions. So when you're listing or finding the interval where it's increasing, if you read it from left to right, starting on the left, this piece here is going up. Because I'm starting on the left and it is moving up. Even though there's a little arrow pointing down, that arrow just says it goes on forever. If I look at another place that it's increasing, at this minimum, its turning point, it's now moving up. So from left to right, any location on the graph that moves up or increases, we want to describe what that interval, that horizontal distance would be. So can somebody give me the first interval on the left? It is increasing. What would the horizontal distance of that increasing portion be? And?
-infinity to -1.
So he said -infinity to -1. So we're using x. That x horizontal value is the distance. It starts at -infinity because it's going to start increasing right away on the left side, and then it stops at -1. Because that's a turning point, it gets a parenthesis and not a bracket. Because that's the point where it increases but also decreases, and it can't really do both. So the 1 would not be included, it's just the max of the graph. So that's considered a max. It's where it stops increasing and becomes a decreasing value. It'll never have a bracket around it. It's the max value, the highest part of the graph. So it's not increasing or increasing. How about the other increasing section? Because there is one other section that's increasing. Emma, what's the other section that's increasing on here? Where's that start?
Starts at 1 and goes to positive.
Right, it starts at 1 and it goes to positive infinity. And again, you're describing the horizontal distance for the x that's happening. So even though, yes, it's going up, we're not using y values, we're describing that distance horizontally. So the two increasing intervals are from negative infinity to negative 1 and positive 1 to infinity. Those pieces are going up. And that means then that the part that's decreasing, Abby, what part's decreasing? Yeah, from negative 1 to 1. And again, both of those are parentheses. So the max tells us where it stops increasing and becomes a decreasing part. The min also tells us that value. So the max and min are used to help us describe increasing and decreasing intervals. Questions? So down below, just a little refresher about max and mins. So relative max and mins. If you have a graph that looks something like this, we graphed them a little bit last year, or something like this. There's an actual max value and a min value, and that would be infinity and negative infinity. Because every graph, as long as it's continuous, goes on forever. So these graphs have a max of infinity. The other graph has a max of infinity and a min of negative infinity. That's the true max and min. However, a relative max and a relative min are the more interesting points of the graph. So those would be either the lowest or the highest points of that curve in your graph. And there could be multiple relative max and mins. So here we would have a relative min because it's the lowest point of that curve. Over here we have another relative min because again it's the lowest point of the curve. It doesn't matter that one is lower than the other. They're both relative mins, Emerson.
Oh, that was good.
Okay. So you're not looking at the lowest of the two, they're both the lowest of that area, that section of the curve. So both of them are considered relative mins. They're both the lowest point of the curve. The max in this case, the relative max, there's just one. Because it's the highest of that. So depending on what the power of your graph would be, you could have multiple relative max and multiple relative min values. Generally, the relative part is just cut out and we just say find the max and min, but you're actually finding the relative max and the relative min with respect to the lowest point of the curve in the area you're looking at. So over here, it would be my max and min. So max is at the peak, and min is in the valley, the lowest point of the valley. Questions? So using your calculator, we're going to see if we can find a max and min. Right now, there really isn't any other way for us to find a max and min, a relative max and min, without using the graphing calculator. Next year in AP Calc, you will be finding those values. So there's things about integrals and derivatives and how they help you find information with the graph. But just a little review with your graphing calculator. So we have negative x cubed plus x. So if you take out that calculator, go to y equals negative x cubed plus x, and then hit graph. There we go. So I have kind of like a backwards curve here. It's decreasing first, goes down first. Right here, it looks like it's going underneath the x-axis and then slightly above the x-axis, but it's a little hard to tell. So if you use the zoom feature and just hit zoom in so that we can see what's going on with the center of the graph where the curves are existing, because that's where a relative max and a relative min appear. So we want to see like what is going on at that area. You don't have to move your little cursor. Right now it's going to zoom in at 0, 0. So whatever it says down here is where it zooms in to your graph. So if you move the x and the y, then it's going to zoom in on that portion of the graph. So we just want to zoom in the center because that's the area where it looks like the curve is kind of happening. And now you can see that there is more of a curve there once you zoom in to that piece that you're looking at. Does anybody remember how to find the min or the max with the calculator? Mason, how do you do that?
Use second trace max or min.
Yeah, so second trace, either one, depending on what you're finding, max or min. So we find the minimum first because it's on the left side of the graph. Remember, left bound means the little blinking cursor needs to be slightly left to the left of the lowest point. So right here's the lowest point. The little blinking guy needs to be on the left side of it. You hit enter. You move the little blinking guy so that it's slightly to the right of it. You hit enter, and then you let the calculator do the work. There we go. So my minimum value is at negative 0.58 and 0.38. So draw a little sketch here. So negative 0.38 and 0.58. That's our minimum. And then going back to the calculator, doing exactly the same thing except finding the max. Move the little blinking guy over to the curve and make sure that it is on the left side of the highest point. So it's now to the left of the peak. And then right bound, I want to make sure that it's to the right of the curve. And then let the calculator do its work when it guesses, and then it gives us a value of 0.58 and 0.38. I think both of these should be negative here. Do I have mine flipped?
Yes.
Yeah. 0.58 and negative 0.38. There we go. And this is 0.58, 0.3. So if you don't know what a max or min is for the calculator, but you're asked to get a decreasing or an increasing value, you must have a max and a min to know where a graph is increasing or decreasing. You can't just guess. Like, oh, well, it looks like it goes up to 1. So you need to know what the max and the min are to be able to say this graph decreases until negative 0.58. This graph over here decreases again at positive 0.58. But you need to know those in order to get an increasing or decreasing interval. So a max and a min actually creates the increasing, decreasing values. That tells you when it starts or where it stops. Any questions? So the last thing that we're going to do then is talk about functions being, just not working today, even or odd. So we know that numbers are even or odd. If it's an even number, what's the rule about even numbers? Why are numbers even? What makes them even? Yeah, they're multiples of 2, it's divisible by 2, that's why it's even. Odd numbers aren't divisible by 2. So functions are also considered even and odd, either based off of the way they look, or based off of a little like even oddness test that we could do. So like you could do an oddness test or this even test to say algebraically if it's even or odd. I know it kind of sounds a little weird to talk about a function being even or odd, but they can be even or odd based off of the way they look or based off of a test that we can perform. So for every even function, if a function is even, if you have your original function and you make the x negative, If it simplifies algebraically to become the same function, then we say that it's even, and I'll show you what it looks like. But essentially, your function remains the same when you perform this algebraic test. If that happens, then we say that it's an even function. Every even function has y-axis symmetry, and that's why the graph is on here. So if my function is symmetrical, and I'm just drawing a picture, I'm not going to plot points, but if it's symmetrical about the y-axis, it's also called an even function. So if it has y-axis symmetry, it's an even function. If I perform this test by making the x's negative and it goes back to my original function, then it's also an even function. So we can look at it graphically, we can look at it algebraically. Odd functions, if I perform this algebraic test and make x negative, if the whole function then becomes negative, then we say it's odd, meaning all the signs have to change from positive to negative in the function. So algebraically, we're going to take the x's, we're going to try and make them change by making them negative. And then if we simplify algebraically and they all remain negative, then we would say it's an odd function. What kind of symmetry do you think odd functions have?
X-axis.
X-axis. Anyone else? If it had x-axis symmetry, think about it. If something's symmetrical about the x-axis, that means the x-axis would cut it in half. What's wrong with having x-axis symmetry, Greg?
Then it would be function.
It would be a function. So x-axis symmetry wouldn't be a function. So it's both of them. We call that original symmetry. So if it has original symmetry, it's really like having both parts. So it has x-axis and y-axis, but that's called original symmetry. So a graph that might have original symmetry would kind of flip. Let me move that one up so that you can see. I'm going to put that right up here. You can see it flipping over the origin. So the origin makes it flip. One side is reflected over the origin to get the other side. If it is an even or odd, then you're going to kind of have a mix of the two. It would have no symmetry. There isn't really a test, but you might have one sign change and the other doesn't. But not all of them, we'll say. Or 2 of the 3 signs change, but you still have one that doesn't change. So a graph that wouldn't have symmetry, maybe it starts somewhere on the other side. So the graph may be symmetrical, like a parabola is symmetrical, but it's not symmetrical about the origin, or it's not symmetrical about the y-axis. So there are really only 2 types of symmetry to say a function is even or odd. It's either y-axis or the origin. If it's not one of them, then it's not even and it's not odd. It's just neither. Questions? So really there are a small group of functions that are even, a small group of functions that are odd. Most of them are even, because they're not going to have the symmetry about the x and the y-axis. So I believe there are 3 functions down at the bottom. And it says determine if they're even or odd. So the one thing you could do would be to plug this in your calculator, which is fine. You can plug it in your calculator as long as you have a supporting graph. That's valid for work. Don't just write even or odd. So tell me why you're saying even or odd. The other thing we can do is the algebraic test. So I want to show you how that test works. So we have g of x. So the test says that if it's even or odd, if you make the x values negative and then simplify it, you have two things to compare to. Is it exactly the same that you started with, or do all the signs change? So just to kind of show you how that works. If I take my x and make it negative, so it's like we're evaluating this function by plugging in a negative x. So instead of having x, we made them negative. Emily Rossi, what happens when you have a negative x cubed? It becomes negative x and it's cubed. And then Emily, if you have a negative x, it becomes plus x. So Emily, if you compare that to the original problem, what would you say? All the signs changed. So we started with x cubed, we now have negative x cubed. We started with negative x, we now have positive x. So all the signs changed. Therefore, this is an odd function. If you graph it, it should have symmetry about the origin. So algebraically, make the x's negative and then simplify. Emerson.
Isn't it? So couldn't you potentially find that it's odd just by the fact that the power that it's raised to is odd and the power of even functions are even?
Not necessarily, because if it doesn't start, like if it doesn't go through the origin, it's not going to have original symmetry. If it doesn't go through the y-axis, if it doesn't cut it in half, it's not an even function. So if this graph said x
Yeah,
minus
so if it's
2
moved to the
squared,
right,
so if
then
it moves
either
left or
odd.
right, it's neither.
Go home.
So yes, Emerson is correct in that if the power is even or odd, that might help you determine if it's even or odd, but not just because of the power. So just because the power is cubed doesn't mean that every cubed power function is odd. So if it shifts anywhere to the left or the right, it doesn't go through the origin, then it wouldn't have original symmetry. Other questions? So looking at letter B, just doing this test here, if we plug in a negative x squared is just x squared because negative times negative is positive. It doesn't affect the 1 is totally separate from it, so this one would be even because it's back to the original function, so this remains the same. So this is even. And then the last one says f of x equals x cubed minus 1. So we have negative x cubed and then minus 1. So the x becomes negative, but the minus 1 stays the same. So even though this power is cubed, it is not an odd function because it doesn't go through the origin. So this would be neither even or odd. So tonight's homework, there's a lot of graphs that you'll be looking at. Please, if you're using your calculator, graph it on your page. Show a little supporting work so that you can kind of support your answer. Have a great day.
I take pictures of this book that I have.
Yeah.
I have.
Would it